So it's my pleasure indeed to present today some results which are really recent. They will appear soon in Nature Communications on the transition to synchronization of network dynamical systems. They are very general, and I hope they will stimulate, in a sense, some discussion among us. So let me start by saying that synchronization is indeed a very old problem in physics. It goes back to Christian Huygens, that is, you see here, mid of the 16th century, 17th century. And he discovered actually that when you take two pendula and you hang them, you're making this pendulum, you put this pendulum in this hanging at the same wooden beam. This pendula, no matter which initial condition you start them from, are actually operating in a collective state, which is in antiphase. They are doing like this. I don't know if you see my fingers. So Christian Huygens actually called this sympathy, not synchronization, but the fact that if you have tiny forces that are transmitted and they are interacted by these forces, the two systems are interacting, the two systems are able to develop a collective behavior. And he understood very well the fact that the reason for the setting of this collective behavior that he called it sympathy were the tiny forces transmitted by the wooden beam from which the two pendula were suspended. Today, synchronization is a very important problem in many issues, and people study synchronization of distributed systems because it has a fundamental roles in natural and man-made networks. Things about brain dynamics, synchronization is at the basis of the normal and, in some case, abnormal functioning of the brain. The heart beating, animal behavior, have this flocking phenomena. People are guessing today that the world climate is indeed a synchronization, a complex synchronization pattern among different regions of the globe. Synchronization happens in the internet, in social science, in human behavior. This is not a conference, but in conference, at the end of the seminar, normally people clap, and this is a clear and evident sign of synchronization. Financial markets are an example of synchronization. Power grids is an example of synchronization. You need to maintain the phase of alternate currency in the system in a very well established path. And there are many, many cases. Okay, so this is a phenomenon that is now being, since I would say 30 years, studied in distributed systems, that is networks of dynamical units. So what we are going to consider, and I jump to the next, is this situation. So we are considering an ensemble of systems. Each node I is a vector. That is, so it's a dynamical system. So you have a state vector xi having m dimensions. We suppose that the systems are identical. So, of course, we need to make some hypotheses to treat in a rigorous way the problem. So all the systems evolve following a given flow f. So fxi describes the unperturbed, uncoupled trajectory of each one of the nodes. And then we imagine that these nodes are networking. And networking, that is, you have a coupling term here, which is proportional to a sigma, which is a global coupling parameter, coupling strength. And we put an explicit adjacency matrix of a network, Aij. So you have here Aij, you have n elements in the ensemble, and we imagine that the systems are speaking each other by means of the output function h. So we are considering this very general case. I can tell you that this is a diffusive coupling, and what I'm going to tell you is by no means limited to a diffusive coupling. There are many, many other couplings, but in order to make things simpler, I will start with a diffusive coupling. So when I have this situation, so an ensemble of systems, all of them identical, which are coupled in a network, then I will tell you what happens in an hypernetwork or in a multi-layer network. But for the time being, let's imagine in a network. What I have is evidently a control parameter, which is the coupling strength, the sigma. And then I have an order parameter. I can measure the level of order that I have in the network. And I can distinguish clearly two phases. One phase that normally occurs at very low values of the control parameters, in which the order parameter is almost zero. And this is the gas phase. That is, all the elements of the networks behave in a completely uncorrelated way. They are not correlated. Each one is almost independent on the other. They are coupled, of course, but the coupling is so small that they are not developing any collective behavior. So it's a sort of gas, like, a Boltzmann gas. This is phase one, and the other phase is instead what happens when the coupling parameter is sufficiently large so that all the element of the network, the systems that are in the network, behave in pace. So they are all synchronized. That means that each node of the network repeats the same dynamics. So it's like a crystal, perfect, order. Yeah. So these are the two phases, so to say, the solid phase, the synchronous phase, and the gas phase, the asynchronous phase. And now the problem is how the system operates a transition from phase 0 to phase 1, or from gas to solid, so solid to gas. There are basically two ways this can occur. One way is go now to the right part of the slide, a first order like transition. That is, I start from the gas phase 0. I increase control parameter. My system stays frozen in this phase up to a moment in which I jump suddenly to the other phase. And I stay then on phase 1. Then I can start my case in phase 1, decrease progressively the control parameter, so I stay frozen in phase 1, and then I jump down on phase 0. Normally, these two transition, the forward and backward transition, can have the same transition point of different transition points, so you can have or not an hysteresis. But what does it mean that in this case you have only these two phases? So your system is either completely unsynchronized or completely synchronized. Okay, so there's no other intermediate phase, intermediate state. This is normally the case that happens in hypergraph. And we will understand why this will happen very soon. When I have graphs instead, that is normal network, I have this other kind of transition, a second order like transition. The transition now from the gas to the solid phase is continuous. It's continuous, it's reversible. It means that if I start from the solid phase and go back, I do exactly the same transition. And this means that there is a huge range of control parameters in which the state of my system is neither a solid nor a gas. It's an intermediate phase. And so the issue is, what is this phase? Because the two phases, the gas phase and the solid phase, are very trivial. In both cases, there's no complexity. In one case is pure disorder. In the other case is single system, repeated n times. So what is this situation, which is the most interesting part, of course, of the game? And this is done by clusters. It is, the system starts to have groups of nodes, or particular nodes, which may synchronize among them. And this state can coexist with the rest of the other systems which are unsynchronized. Or two groups of synchronized clusters can merge and form a larger synchronized unit. Or I can nucleate another synchronized cluster. So I have several events which involve synchronization limited to specific nodes or groups of specific nodes, called clusters, or group of specific clusters in the network. And an enormous quantity, therefore, of questions arise. How can I individuate the nodes which form such clusters? Can I calculate and predict exactly at which time each specific cluster will be formed? Can I predict the sequence of these events during the transition? Can I individuate, which cluster is more synchronizable than the others? In general, how can I treat this problem? And this, our work solves completely, of course, under a small approximation that we will see immediately and under the hypothesis that the systems are identical, the problem. So in order to solve this problem, I need to make three different steps. The first step is something that was done actually 24, 25 years ago, which is the master stability function. That is, let's suppose now to consider this network of dynamical systems, which I already described, and let us now assess the conditions for stability of the solid phase. That is, I now concentrate in the solid phase, in the complete synchronization state, and I want to assess the stability of such state. First of all, I can notice that I can rewrite this equation in terms of the Laplacian matrix, because this is nothing but the Laplacian matrix, and everybody knows that the Laplacian matrix of a network is a symmetric matrix if the network is symmetric and has the property of being zero sum. So the fact that the Laplacian is zero sum ensure existence and invariance of the solid phase. So I have a solution x1 equal to x2 equal to xn that I call synchronized solution ST, which obey SFS, because of course, when I put this solution, the network part, the coupling part goes to zero because of this property. And therefore, this solution is independent on sigma. So for each coupling strength, I have the same solution, is invariant. And I can study as a function of sigma, which is the property of stability of such solution. Normally, to study the stability of such solution, what normally consider the perturbations, delta xi, the deviation, how node I deviates from this solution, plug this into the equation, linearize, that is, make linear stability analysis, and obtains equation for this delta xi, which of course include the Jacobian of the function f, the flow, calculated in such solution, and the Jacobian of the output function h, calculated in the same solution. And if one take this big vector delta x, which contains as first m components delta x1, second n components delta x2, and I mean, it put all the deviation together, one can write this equation in block form. Delta x, in direct product jf, minus sigma lambda direct product, sigma Laplacian direct product jh. So this is the main equation one has to consider, which is the equation for the deviation, the linearized equation for the deviation of this. And now one has the following important property. I repeat, I consider the simplest case of a symmetric matrix, that is of a symmetric network. Everything can be extended in many, many things. There are 20 years of studies here, but if the matrix is symmetric, then the Laplacian is symmetric, therefore it's diagonalizable, it has all the eigenvalues which are real, I can order them by sides. And what is important that lambda 1, the first eigenvalue, is 0 because of the zero sum condition. And the associated eigenvector is 1, 1, 1, 1, 1. So all the components are equal. Therefore, this associated eigenvector is exactly pointing to the synchronization manifold in the phase space. So in the phase space, the V1 is pointing in the synchronization manifold. And therefore the tangent space, the perpendicular space to V1 is spanned by V2Vn, because this is an orthonormal basis, and therefore V2Vn are spanning all the possible direction of the phase space which are orthogonal to this. So what I want for stability is that this manifold be contractive, be absorbing, and therefore I want that in all the perpendicular direction I have contractive properties.
May I interrupt?
So
May I
please,
ask something? Just
please.
for the matter of understanding, when you mention here the synchronization manifold, do you mean that it has a continuous property, so it's discrete?
For the time being, we are considering it to be a continuous
Okay, thank
manifold.
you.
But we can extend I repeat, I'm treating now the simplest case for illustration. Then if you want, I can tell you the various directions where this was expanded. But for the time being, let's consider a continuous flow, okay? So I have this, and so normally what I do, I take this big error, I write this as a linear combination of the eigenvector of the Laplacian, and I have this coefficient Xi, therefore, and I can write equations for this coefficient Xi that, as you see, are JFS minus sigma lambda I JHS Xi. So these are variational equations in the sense that the derivative in time of Xi only depends on Xi, not on Xj, J different I. And if I take two different I, the only difference is lambda I, the particular value of the eigenvalue. So here the genius idea of Pecora 20 years ago was, I can therefore disentangle the structure and the dynamics, because I can take now one parameter nu, which is sigma lambda, and just study the property of this variational parametric equation. You see, this variational parametric equation, which is JF, JH calculated in the synchronous solution, only depends on F and H. So only depends on the dynamics, on the flow, on what describes the dynamics of the local units, and on the output function. And then I can study this as a function of nu. Therefore, the maximum Lyapunov exponent of this as a function of nu is called the master stability function. Okay? Now, when I study this function, each network will be just a collection of points in the x-axis, because it will be nothing but a collection of eigenvalue of the Laplacian matrix, so specific values of nu. So they're called master stability function because this function gives stability for all possible networks of this specific system and this specific function. And now let me tell you what is the story. So if we consider chaotic systems, so what is the value of the master stability function at nu equal to 0? The value of the master stability function at nu equal to 0, nu equal to 0 means lambda is equal to 0. So it means we are in the synchronization manifold. So this function starts at nu equal to 0 from the maximum Lyapunov exponent of the single isolated system. So if I have a network of Rössler oscillators or Lorentz oscillators in a chaotic regime, this is positive. If I have a network of periodic systems like, Kuromoto, that's 0, because the maximum Lyapunov exponent of a periodic system is 0. So let's suppose now it's chaotic. So I have a network chaotic system. So this function starts from some value which is positive. And then whatever choice of system and output function, you have three classes, three possibilities. Class 1, the master stability function never crosses the x-axis. For example, it's all monotonically increasing. Or it can go down and up, but it never crosses the new axis. So all the systems, FH, which belong to this class, intrinsically define synchronization, because no matter which network you use to couple them, the synchronous behavior, the solution, the solid phase, will be always unstable. You take any distribution of points here, you find the direction transverse to the synchronization manual to be associated to positive Lyapunov exponent. So you don't have contraction, you have always expansion. So systems in class 1, problem solved. There is no synchronization, no solid phase, no clusters, nothing. Class 2, there is one intersection with a new axis, and this intersection defines a critical value nu star. Class 2 systems are the opposites of class 1, are systems that are always synchronizable. Why they're always synchronizable? Because it's sufficient that you take the coupling strength, sorry, here is written D, is not sigma, D is and sigma are the same. And you multiply D by the second smallest eigenvalue, lambda 2. And you make this value larger than nu star, then of course d lambda 3 will be larger, 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 and then you have all the direction transverse to the synchronization manual contractive. So the condition for synchronization in class 2 is that you need to have a critical coupling strength D, which is nu star divided by lambda 2. So the critical coupling strength in class 2 is renormalized by the second smallest eigenvalue of the Laplacian, which is the connectivity. Okay? So class 2, you can always synchronize. Class 3 is when you have two intersections, nu 1 star, nu u star, nu 2 star. Now the situation is a little bit complicated because you need the entire spectrum of the Laplacian multiplied by the same D be inside the region where the master stability function is negative. So you need not only that d lambda 2 is larger of this nu 1 star, but you need it from the same d lambda n be smaller than this. Otherwise, you have some direction which escape this curve and correspond to some expanding direction, some unstable direction. So this means that the class 3 are more complicated because now the structure of the network is fundamental. That is, you have networks that may synchronize these systems and networks that instead are unable to synchronize these systems. Okay? So this is for the solid phase. And for the solid phase, we can therefore classify the network. So you give me the system, Rösler-Lorentz, you give me the output function, the identity, sinus, cosinus, whatever, how they interact. In 1 minute, I calculate the master stability function. I can tell you if you can synchronize, you cannot synchronize, how you can synchronize, how you can construct a network for synchronize, and these things. This is step number 1. Now, in fact, we have proven in our nature communication that when you study any cluster synchronization structure, which is you're not studying a solution x1 equal to x2 equal to xn equal to something, but you have studying a solution in which some nodes are equal and some other are not equal. You end up exactly with this same structure. The only difference being that now here the Jacobian for calculating the maximum Lyapunov exponents must be evaluated in the new solution, in the cluster synchronized solution, which is perturbed by the fact that here, when you couple them, this term will not be 0 anymore because you will have an additional term due to the fact that these nodes are interacting with other nodes which are not synchronized with them. We have evaluated how much is this deviation, and let us make zero-order approximation, deviation 0. So let us make an approximation, the first very rough approximation, and we will see that instead it's a very good approximation, that as soon as you consider sparse networks, then you can refer always to a unique master stability function for whatever cluster synchronized solution you consider. And this, of course, is an approximation, because if you want then to calculate exactly the value of mu star for which you have this, you have to slightly tune this curve due to the fact that you have this additional term. But let's forget additional term for the time being, and let's consider, therefore, the case of unique path to synchrony, unique solution. Class 1, I already said there is no synchrony, there's nothing. Let's therefore consider class 2. I can tell you that class 3 is exactly the same as class 2. So now we consider class 2. The second step we have to do is to unfold the transverse space. What does it mean, unfolding the transverse space? It means that imagine that you progressively increase the coupling strength. Then what happens? It happens that this axis is d lambda. So these eigenvalues of the Laplacian will progressively cross this specific threshold. Okay? They will progressively cross the critical point. And therefore, at each value of the coupling strength, you can always consider a subspace TD of the space which is perpendicular to the synchronization manifold, which is the one spanned by the set of eigenvectors whose corresponding eigenvalue have already crossed the stability threshold. So this specific subspace will always contain only contractive directions, because it's made of eigenvectors whose corresponding eigenvalues, I have to read the master stability function is negative. And I know the sequence, because the first will be lambda n, then lambda n minus 1, lambda n minus 2, lambda n minus 3. So in the inverse order of their sides, I'm feeding this specific contracting subspace. Okay, this is very important. When I increase d, I have a contractive subspace which I can control. I mean, I know how it's made. Second point is a stupidity for mathematician, but not as much for physicists. Normally, what you do is you define a matrix V in which the eigenvectors are taken as the columns. And if you do so, you can observe immediately the following, that the eigenvectors are orthonormal, and therefore, if the eigenvectors are orthonormal, that you have that V transpose is the identity. But then, this means that V transpose is V minus 1. Therefore, the identity that you can write V minus 1 V is V transposed V. So V transposed is equal to V transposed V. Or if you want, V commutes with V transposed. Or if you want, the rows of this matrix provide an orthonormal basis as well. But now let us dig a little bit on this property, and let's examine the eigenvectors component-wise. So you take the eigenvectors, Phi, and to each eigenvector, you associate these matrices E lambda I, which are nothing but taking the I and j component of the eigenvector, comparing them and squaring. See, component 1 minus component 1 square, component 2 minus component 1 square, component n minus component 1 square. Here you have 1 minus 2, 2 minus 2, n minus 2. then 1 minus n, 2 minus n minus n squared. So this is a function only of lambda I, because it depends only on the components of the eigenvector vi. These matrices are, of course, symmetric and the diagonal elements are 0 by definition. Then, starting from this, we construct a sequence of matrices Sn. So we take Sn plus 1 equal to the 0 matrix. Then we take Sn equal E lambda n. Sn minus 1 is E lambda n plus E lambda n minus 1. Then we sum E lambda minus 2, E lambda minus 3. So we sum sequentially this E lambda in the same sequence at which the eigenvalues are passing the critical point, so are entering the contractive space. So you have Sn, Sn minus 1, Sn minus 2, blah, blah, blah. Now, one important thing, how much is the maximum value that an entry can have in these matrices Sn? The maximum value is 2. Why? Because these are orthonormal vector of norm 1. So when the two vectors ij are perpendicular, then this matrix is nothing but, you see, taking the I column, the j column, the I row, the j row of this matrix as two vectors, making the difference of this vector modulo square, and limiting this vector to the last components, because only when I have S1, I have the sum of all components. So when the two vectors are orthogonal, the difference vector is square root of 2, and therefore the square is 2. So the maximum entry I can have here is 2. And since the basis is orthonormal, when I get to S1, so I'm summing all the components, I will have a matrix. S1 will be 0 in the diagonal and 2 everywhere else, because I take any 2 row here, ij, make the difference square, I have 2, because they are orthonormal vectors. Okay, so that's very important. So the off-diagonal elements of the matrices Sn are nothing but the square of the norm of the vector, obtained as the difference between the two one-norm vector defined by rows I and j of matrix V, limited to their n last components, and as so the maximum value can be only 2 when the two vectors are orthogonal. Okay, let's now go to the third step and final step. The final step is understanding that the formation of a cluster corresponds to a specific property of the eigenvectors of the Laplacian. And in order to do this, I need here to define what I intend for block localized, a spectral block localized set. So I take a subset S of k minus 1 eigenvectors of the Laplacian. This subset is labeled by I1, Ik, which are k indices, as you will see why this is. So the subset S I1, Ik consists of k minus 1 eigenvectors of the Laplacian, and it is said to form a spectral block localized at the nodes I1, Ik if each eigenvector of the set has all entries except I1, Ik equal to 0. So the eigenvectors are localized in the sense that the components outside those indices are 0. Inside, they have some component different than 0. And for each other eigenvector that does not belong to the subset, the entries I1, Ik are all equal. So this is the definition of a block localized set. And now our theorem. The two following statements are equivalent. So it's a if and only if. So the statement number one is, we have k nodes that belongs to a cluster that is defined by indices I1, Ik. And these k nodes have the same connections with the same weights with all other nodes of the network. Therefore, if I take any two indices PQ that belongs to I1, Ik, and any index J that does not belong to I1, Ik, we have that the Laplacian entry Pj is equal to Qj. This means that this subset of nodes, I1, Ik, they are indistinguishable from the eyes of any other nodes in the network. They receive the same input from the rest of the network. So they are forced by the same input. And therefore, they are potentially synchronizable, because same input means same output. Now, this means that you have a sort of dynamical equitability. Okay, so these nodes are receiving during the dynamics always the same global input from the rest of the network. So this is statement number one.
Yes,
and this
sorry to interrupt you, just because we want to have time to discuss. That's why I wanted to make sure about the timing.
10 minutes.
Yes, 5 minutes.
10 minutes.
Well,
statement number one is equivalent to, we have a spectral block S I1 Ik of k minus 1 Laplacian eigenvector localized at node I1 Ik. So here we are saying that the cluster we will see during the transition are nothing but they corresponds to the formation of spectral blocks in the Laplacian matrix. Now, I don't have time to discuss the consequences of the theorem. This means that clusters are not symmetry orbit, are not equitable partitions, are blah, blah, blah. I want to go to the conclusion. We can cook a cake, which is very powerful. We can take a network, consider the Laplacian matrix, extract eigenvalues, order them in sides, extract eigenvectors, calculate the matrices E lambda I Sn. And then starting inspecting the matrices Sn in the same order with which the Laplacian eigenvalues are crossing the critical point. N and minus 1 and minus 2, blah, blah, blah. What happens when for the first time in the sequence one see an entry equal to 2? It means that there is a block localized structure, because if the corresponding vectors are already orthogonalized for this subset of components, means that there is a spectral localized block. And therefore, I have individuated a cluster that occur in the transition, because this spectral localized block will occur always inside the subspace which is contractive, because I'm using the sequence for which I'm entering the contracting region. I can therefore make a prediction, cluster or clusters, depends, will be formed, will synchronize. I can even predict the coupling strength value, which is nu lambda p, where p is the value at which for the first time I see the entry equal to 2. And then I can span the entire sequence Sn and reconstruct entirely the sequence of events that I have in the transition. I want to make you an example, because these things are clear only with an example. This is an all-to-all connected network. These are weights that you put in a way that you have 3 clusters, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. See, for example, node 7 to node 4 is 0, 5 to 9. Node 10 to node 4 is 0, 5 to 9. So this element is equal to this. You can, I mean, they are verifying statement 1 of the theorem. So 10 nodes, you can take the Laplacian, blah, blah, blah. You have 10 matrices, okay? S10, do you see anything equal to 2 here? No. Then we go to the next, S9. Do we see anything equal to 2 here? No. S8, wow. First prediction. When the coupling strength will be nu star divided by 6003, which is the corresponding value of the eigenvalue, the first event in the transition is that a cluster will appear formed by nodes 7, 8, 9, 10. Ahead, S7, additional elements equal to 2? No. S6, additional elements equal to 2? No. Wow. Second prediction. When nu star is equal, sorry, when the critical, the coupling strength is nu star divided by 4003, the cluster with node 4, 5, 6 will join the one 7, 8, 9, 10. Then continue. Additional no. Then, of course, when nu star divided by lambda 2 is in class 2, the definition of the solid phase, so everything becomes synchronized. So you see that inspecting only the Laplacian eigenvalues eigenvector, you have the entire description of the transition, which means that this is universal, is independent on the specific dynamical system. This is the strongest part of the game. So this is the prediction. You have first this cluster formed, then this joins this, and then all cluster join. You make simulation with Lorentz, with Rössler, and you see exactly this. The first, this is the synchronization error going to 0. So the first cluster that forms is the one that you predict.
Just to make sure that, because some people have the following meetings, and if you want to discuss, maybe we can ask already some questions. I'm really sorry, it's just that I need to.
I have only 3 minutes left. Please, let me only conclude, and then I get to the point. So this is D1, D2, D3. So the exact transition is predicted, and this is valid. Then you can, of course, do the same for larger size networks and so on and so forth. You can do the same for the power grid network of the United States. So you take a real world network, you calculate the Laplacian, you predict the exact sequence of synchronization that you experience in each one. So in practice, you have this state. So since now Lyubov is okay, so I want to finish here. There are many imaging questions he wants to make. So let me go at the beginning, and I'm open to questions.